Hey everybody, it's Mr. Molikash. Today we're going to be talking about what we call improper integrals. Let's see if I can get these tools working today. Improper integrals kind of begs the questions, what are proper integrals, right? So up until now, if you've been doing a definite integral, like something like the integral from 0 to 1 of x dx, right? This, I would consider this a proper integral because the way to do this is use the fundamental theorem of calculus, right? And then just put in, your limits, right? So then you put in 1, and then you put in 0, and you subtract the results, right? So that's kind of how that works out. So what if one of the limits of the integral, either the lower or the upper limit, was something that when we put into the antiderivative, difficult to evaluate, right? So, something like this. What about the integral from 0 to infinity? Like, how would we even do that? Well, one way to kind of think about this is, you're looking at a graph. The graphical representation of this integral would be, the line y equals x, excuse me, and then you'd start at 0, and then you'd calculate area under that curve forever, right? And so the question is, like, how much area is there? And there's an infinite amount of area. So whenever there's an infinite amount of area, we say that the integral diverges. And I'm going to show you what that means analytically with just working it out by hand instead of graphically, okay? So let me go erase stuff, and we'll kind of go. Still trying to figure out how to use this tool here. I ran out of free trials on the Notability app, so trying to see if I can maybe scroll the pages or something on this. Not really sure, how that's working out. I can't really make. I guess what I just need to do is just keep making more pages with that tool up there. All right. Well, anyway, the way to do this analytically would be to still calculate your antiderivative, and you still have x equals 0 as your lower limit, which is fine, right? You can put x equals 0 in there, but you can't use x equals infinity. You can't do that, right? So what we need to do instead, right here, is put a placeholder for that infinity symbol. I'm going to call this b, okay? And then what I'm going to do, let me move this equal sign over, I'm going to calculate the limit of this expression as b approaches infinity. And it's not going to be hard to see that when I do this, right, I'm going to do the limit as b approaches infinity of what? B squared over 2 minus 0 squared over 2, which is infinite, right? So what this means, we can't say that the integral equals infinity. That doesn't make sense, but the limit is unbounded. So we can say that the integral diverges. Okay, I'm going to show you an example or two, maybe even more than that, of some integrals that don't diverge, that converge, which means that they're, even though the amount on the x-axis is infinite, the limits are infinite, the amount of area that you're calculating isn't, which is kind of bizarre, right? So let's go to another page. Here we go. Okay, I figured it out. So here's an example that's in the text. So we'll do the integral from 1 to infinity of 1 over x dx. And the way that we're going to do this, of course, is use the power rule. right? So, oh no, we can't use the power rule, can we? Nope. That is our natural log function, isn't it? Okay. So what I'm going to do, though, is formally write out what this is. It's going to be the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. And we know that the antiderivative of the integral of 1 over x, the antiderivative is the natural log, right? So that's going to be x equals 1, and then x equals b, right? Because b was our upper limit. Okay, and if we do this, we're going to have to figure out what happens to our natural log function as the b gets infinitely large. And of course, the natural log of 1 is 0, right? So the natural log of 1, we can ignore that because that's 0. And if you remember what your natural log function looks like from pre-calculus, off to the right side, there's a vertical asymptote at x equals 0. But off to the right side, the range is unbounded, right? The range is infinite. So the bigger the b gets up there, the bigger the b gets, the bigger the natural log gets. So this diverges. This diverges. Okay. All right. So what I'm going to do is change this problem to a different problem and show you one that doesn't diverge. Okay. So let me erase. Oh, actually, I undo some stuff. Again, be patient with me. I'm still trying to figure out these tools and the right tool to use for these videos and all these kinds of wonderful things. But I'm just going to back up a little bit. And I'm going to get a different function in the integral here. And this time, I think what I want to do is let that be, whoops. There we go, 1 over x squared. 1 over x squared. And this is the one where we definitely can use the power rule, right? This is going to be the limit as b approaches infinity of our integral from 1 to b of x to the negative 2 dx. So what that's going to wind up being is the antiderivative is going to be x to the negative 1 over negative 1. This is the formal way to work this out, right? I'm going to try to clean that up a little bit. We now know that x to the negative 1 is a fraction, right? So that's just going to be negative 1 with b put into it minus negative 1 with 1 put into it, right? And again, the expression here in the brackets is really just negative 1 over x, which is the reason why I'm writing this, okay? All right, so what happens to this expression in brackets? Well, as b gets infinitely large, this fraction goes to 0, right? And then minus negative 1. So the answer is 1. And we can say that the value of the integral converges to 1, which means that if you were to look at the graph of 1 over x squared from x equals 1 to, well, forever to the right, the amount of area in here gets closer and closer to 1 square unit. Even though you keep going forever to the right, the amount of area is limited, is bounded. And so that may blow your mind a little bit, right? You have a finite amount of area with an infinitely long fence around it, which is kind of bizarre, right? So that's what it's like with improper integrals. Try to do another example here, because you don't have to have infinity. You don't have to have an infinite boundary for your region. So here, let's just do this one. do want to mention the fact that when you're doing an integral, right, when you're finding the antiderivative, we now have all different techniques available at our disposal, including partial fractions, integration by parts, using completing the square, lots of different things that we can do to find antiderivatives. And so part of this process is finding the antiderivative. The easy part, of course, is just finding the limit, right? Finding the limit. All right, so let's figure this out. In this fraction, the integrand, the function that's being integrated, if x is equal to 0, there's a problem, right? On the graph of this function, whatever this looks like, and x can't be negative in this fraction either because you'd have imaginary numbers in the denominator, right? So you got this kind of thing going on where you have x equals 0 as a vertical asymptote, right? And we're trying to figure out, okay, when we get to up to x equals 1, how much area is there? But the region is unbounded on the y-axis side, right? And so we're going to, basically we're asking the question, how much area is there here? Okay. And we can find out by just computing the antiderivative and plugging in our limits and finding the limit, right? Okay, so this is going to be the limit as b approaches 0 from b to 1. And I'll just rewrite this as x to the negative 1/2 so we can use our power rule. But I hope you understand why b has to approach 0, right? It's super important. B can be 1, right? I could have plugged 1 into this function just fine, but putting 0 into it causes a problem, right? Okay, so what we're going to do is find our antiderivative. Ho-hum, same stuff we've been doing, right? So that's going to be x to the 1/2 over 1/2. And that's going to be x equals b to x equals 1, right? Using the fundamental theorem of calculus. And let's clean that fraction up a little bit. We'll just rewrite it in a different form. So dividing by 1/2 is the same thing as multiplying by 2 over 1, right? So this is 2 times the square root of x is what our antiderivative is, right? And putting 1 in there, we get 2 times the square root of 1. And putting b in there, well, what's the limit as b approaches 0 of 2 times the square root of b? Well, this is just 0, right? In fact, you can just plug 0 in there to find the limit. So you get 2 minus 0, which is 2. So I feel like I did something wrong, but I hope I didn't. If you're interested in kind of wrapping your brain around what's going on with a calculator, I can just use Desmos calculator a little bit. And I can graph this, right? I can graph this function 1 over square root x. And I can even do an integral, right? INT is the integral, right? And I'm going to put a b down there, and I'm going to put a 1 on the top. Let me make this a little bigger for you guys to see. All right. Of that function. And I have to put my dx there, right? Okay. Now, I'm going to want my upper limit to be 1. And I want my lower limit to be very, very close to 0, right? And I'll make this really, really small, like 0.05 or something. Okay. And you can see the value of the integral. The closer that b gets to 0, right, the answer is getting closer to something bigger than 1, right? Something bigger than 1. And if we make our steps even smaller, whoops, it's Desmos is telling us that, hey, it's really, really close to 2, right? But in fact, if you just put the number 0 there, you get 1.99999, but the actual answer isn't 1.9999928. Desmos is actually wrong because it has this round off issue, right? So if you're trying this on Desmos calculator or something like that, you'll probably get a slightly wrong answer. And in addition to that, if you do one that diverges, right? So let's put one in here that diverges. And I haven't done this one, but this one's going to diverge, right? It's going to say undefined. And so you, as a student, really need to know why it's undefined or what that means in context, right? Okay. One more example, and then we'll kind of close up shop here. And this one's going to require some remembering of things about inverse trig functions, right? So this one is going to be doubly improper. It's going to be the integral from negative infinity to infinity. And this is going to be, hopefully you remember the antiderivative of this. But this is doubly improper, right? So technically speaking, we'd have to create two integrals. We'd have to split this up into the integral from negative infinity to a certain number, and then the integral from that same number to infinity. Another way we can do this is we can just say, hey, the limit as b approaches infinity of the integral from negative b to b. So what is the antiderivative of this function? Hopefully you recognize that as the inverse tangent function, right? Or hopefully arctangent. You've been writing that by now. The arctangent. Okay, so what do you remember about the graph of the arctangent function? Do you remember? Sorry, I'm trying to spell all this out. So in the arctangent function, what's going on is you have two horizontal asymptotes, right? The top one is at pi over 2. So that's what the limit of this one is, right? As x gets infinitely large, the value of the function approaches pi over 2. Okay. Now, there's another one down here. As x goes off to the left, we have a different horizontal asymptote, which is negative pi over 2. And then, of course, subtracting a negative means adding a positive, and 2 pi's over 2 added together make pi. Right? So the answer to that one was pi. It's kind of interesting, huh? So there's the work for that. Feel free to slow this video down or rewind or pause if you need to. I'm going to go back to my Desmos calculator here and kind of show you what's going on there graphically. So I'm going to graph that function. Okay. And let me zoom in a little bit. And I'll make the y, go up to, I don't know, about 2. And we'll make the x-axis, pretty long. Okay? All right. All right. And then what I want to do is I'm going to limit the domain here to negative b less than or equal to x less than or equal to b, and then I'm going to create a slider for b. Oops. Okay. So if b is 1, you get that amount, right? Oh, almost forgot. This should be less than or equal to here. There you go. and it should be above the x-axis, so there we go. All right. So how much area is there right there? Well, the way to find that out is to calculate the integral, right? So we're going to do the integral from negative b to b of this function. Now, I don't know if you remember what the arctangent of 1 is, but that's pi over 4, right? Tangent of pi over 4 is 1, so the arctangent of 1 is pi over 4, and that means that we have pi over 2, which is 1.570, whatever. Okay, so what if we make this, and, doesn't make sense for the integral to be, going from negative 0 to 0 or whatever, but we'll just stop there and we'll go up to 10, see what happens. Okay, so the integral from negative 1 to 1 looks like this. The more area we get, the answer to this integral kind of it has a limit to it. You would think that it gets infinitely large, but it doesn't get that big. In fact, we can go all the way to 100 even, and say, okay, what happens if we went all the way, to 100? How much area is there if we keep on going all the way out to 100? It's never going to be bigger than pi, is it? Even if you were to make that 1,000. Getting up to 1,000 is a million. Oops. Didn't mean to ask Siri anything. Sorry about that. But you can see, right, this is really, really getting close to pi. So this is what it means for the integral to converge, right? The amount of gray shaded area under this curve, even though it's infinitely bounded, it has no boundary to the left and to the right, there's a finite amount of area under there. It's not an infinite amount of area. So that, again, that might kind of mess you up a little bit in your head, but it's what's important to know about this is that it's what the antiderivative is doing that tells you the answer, right? If the antiderivative converges, then this integral converges, right? That's kind of what's going on. All right, so again, your steps are find your antiderivative, which, depending on the integrand, can be pretty hard. And then wherever there's a discontinuity or an infinite length interval, right, you're going to have to calculate a limit there of your antiderivative. And that will tell you whether the answer converges or diverges. And if it converges, they want you to find the answer that it converges to. All right, 6.4 in the text is where all this is found. If you're watching this and you're not one of my students and you want access to the text, just message me or email me. I'll give you the textbook link. And hang in there. This is going to be a little challenging, and I want you to show your work. Show your work.